As we move into section 7.2, there's not a whole lot of new ideas, just some new terminology. So we're going to talk about the definitions and general results for eigenvalues and eigenvectors. The first definition that we want to talk about here is for what's called an eigenspace. So let A be an n by n matrix. For a given eigenvalue, lambda I, that comes from A using the technique that we developed in the last section, let E sub I denote the set of all vectors V satisfying the equation AV equals lambda V. That is to say, E sub I is the space, the vector space consisting of all eigenvectors associated with lambda I. Now, not just a couple of vectors, but the span of those vectors. Now, then E sub I is called an eigenspace, this word space meaning that it's a vector space. So then E sub I is called the vector space of A corresponding to the eigenvalue lambda I. Thus, E sub I is the solution space to the linear system A minus lambda I times V equals 0 for a very specific I. So what does that mean? It just means that if you take a collection of eigenvectors that are associated with lambda I together with the 0 vector, they will generate a vector space, and we call that an eigenspace. Okay. The next definition, an n by n matrix that has n linearly independent eigenvectors is called non-defective. Now, we've already talked about this a little bit. In this case, we say A has a complete set of eigenvectors. And if A has less than n linearly independent eigenvectors, it is called defective. So this is related to the algebraic versus the geometric multiplicity, which we'll look at here in one of our examples in this section. As for notes, we have some 5 basic ideas that you guys should internalize and know for maybe some true or false questions in the future. Number 1, the solution to this eigenvalue problem, we're always interested in non-trivial solutions. And so as a result, 0 vector is never an eigenvector, even though it does satisfy this equation. It's the trivial solution, and we're looking for non-trivial solutions. If A is non-defective, then the eigenvectors of A form what's called an eigenbasis for Rn. So let's talk about that. Now, if A is non-defective, we know that it has n linearly independent eigenvectors, and in Rn, that has dimension n, that's going to form a basis. And so not only is it a basis, it's a basis constructed out of eigenvectors, and so we give that a special name. We call it an eigenbasis. So let's make that special by highlighting it, an eigenbasis. So maybe that should have been another definition, but it's just simply a basis created from eigenvectors. Now, every eigenvalue of A has at least one eigenvector. So if you have a standalone eigenvalue, it is always going to generate at least one eigenvector. It might generate more, but it'll always have at least one. And that leads us into the next 2 ideas, eigenvectors corresponding to distinct eigenvalues, meaning if you have 2 different eigenvalues, then the vectors corresponding to those 2 collections are linearly independent as a group. So what does that mean? It means that eigenspace 1 for lambda 1 is linearly independent from eigenspace 2 from lambda 2. Okay. And then finally, if A is an n by n matrix and has n different and distinct eigenvalues, then by default it's got to be non-defective. So why is that? Well, we know that from this last statement, distinct eigenvalues generate linearly independent vectors, eigenvectors. And if A has n distinct eigenvalues, that means it has n different eigenvalues, and each one is going to generate exactly 1, and they're all going to be linearly independent, and therefore automatically A becomes non-defective. So those are just our statements, definitions, and some basic ideas. All right, let's take a look at our first example here. Example, find the eigenspaces and their dimensions for the matrix A equals 1, negative 3, 1, negative 1, negative 1, 1, and negative 1, negative 3, 3. So this is going to start out like any other problem. We're just going to basically find the eigenvalues and eigenvectors, but we're going to talk a little bit differently about our results when we're done. So let's see here. We're going to always start with our characteristic polynomial. That's going to be the determinant of a minus lambda I, which in this particular case will be the determinant of 1 minus lambda, negative 3, 1, negative 1, negative 1 minus lambda, 1, and negative 1, negative 3, 3 minus lambda. Now, that is going to generate the following. It's going to give us the characteristic polynomial negative lambda minus 2 squared times lambda plus 1. In the interest of saving time in this video, if you go through the motions and do that determinant and then factor it, this is what you should get. And so we have a couple of eigenvalues. This will equal 0 if our first lambda value is 2, and that has an algebraic multiplicity of 2. I am referring to the fact that the number 2 makes this factor 0, and the fact that I have a square. So this square corresponds to the algebraic multiplicity. And then the other value is lambda 2, which we're going to call negative 1 here, and that has an algebraic multiplicity of 1. So again, that's the power on that factor. Okay, so these are, again, our eigenvalues, and they are distinct eigenvalues. This one is repeated by 2, however, relative to one another, they're distinct. So the eigenvectors we get from lambda 1 equaling 2 should be linearly independent from any eigenvalue vectors that we get from eigenvalue negative 1 in terms of the notes that we just talked about above. So let's start off with finding our eigenvectors. In case 1 here, lambda 1 is equal to 2, and that means that a minus lambda I is equal to the matrix 1 minus 2, negative 3, 1, negative 1, negative 1 minus 2, 1, and negative 1, negative 3, 3 minus 2. That is equal to the matrix negative 1, negative 3, 1, negative 1, negative 3, 1, and negative 1, negative 3, 1. And the row reduction here shouldn't give us any trouble. I'm going to flip the sign on the first row so that this is 1, 3, negative 1. And then everybody is the same row, and so subtracting row 1 from row 2 or row 3 is going to give me zeros. And I can see here that I have 2 0 rows, and so row 3 can be interpreted as x3 being free. Row 2 can be interpreted as x2 also being free. And then row 1 is x1 is equal to negative 3s plus t. And this makes my vector v for a minus lambda 1 v, a minus lambda 1 I times v equals 0 as v equal to x1, x2, x3, which here is negative 3s plus t, s and t, which we can decompose as s times the vector negative 3, 1, 0 plus t times the vector 1, 0, 1. Now, we have been choosing some very special values for s and t in our previous examples. But what you need to know is there's not just one possible eigenvector or 2 possible eigenvectors here. There are an infinite number of possible eigenvectors. So actually, this expression represents all possible eigenvectors for lambda 1 equal to 2. So we can express our answer in two ways. We could do this, option 1. We can let first s equal 1 and then t equals 0, and that'll give us our eigenvector 1, which is equal to negative 3, 1, 0. We could let s equal 0 and t equal 1, and this would give us a second eigenvector for this eigenvalue, and that would be 1, 0, 1. And then we could say that eigenspace 1 is the span of these two vectors, negative 3, 1, 0 and 1, 0, 1. Or option 2, which really says the same thing, we can just simply say that eigenspace 1 consists of all the vectors of the form s times negative 3, 1, 0 plus t times 1, 0, 1, such that s and t are real numbers. Either way, they express the exact same set, and there's no difference. So in terms of our notes above, we might note here that lambda 1 equal to 2 generated two linearly independent eigenvectors, or has an eigenspace of dimension 2. That is to say, this here is the eigenspace, and this is a basis for eigenspace 1, in which case we can see here that the dimension of eigenspace 1 is 2. The dimension of the eigenspace, this is known as the geometric multiplicity. This is the geometric multiplicity of lambda 1 equal to 2. So one way that you can tell a matrix is defective or not is whether or not the algebraic multiplicity for every eigenvalue is equal to the geometric multiplicity. And in this particular case, we're going to note that the algebraic multiplicity here of this eigenvalue was 2, and the geometric multiplicity was also 2. So if each lambda sub I has algebraic multiplicity equal to its geometric multiplicity, then A is a non-defective matrix. Now, that's just another way of saying the exact same things in the notes and definitions that we had above. Now, I can't actually classify this matrix right away as defective or non-defective. Actually, that's a lie. I can. But what I mean here is we shouldn't jump the gun and say just because this particular eigenvalue had an algebraic multiplicity that was equal to its geometric multiplicity, that doesn't mean the entire matrix is non-defective. I should go check the other eigenvalues in general, but since this particular matrix is 3 by 3 and there's only one more eigenvalue and its algebraic multiplicity is 1, and I'm guaranteed that it's going to generate at least one eigenvector, I can actually tell you right now that this matrix is non-defective. But let's go through the motions here. So case 2, lambda 2 is equal to negative 1, and that one had algebraic multiplicity 1. So I'm guaranteed here that this is going to generate at least one eigenvalue, and it's not going to ever generate anything more than 1 here because the algebraic multiplicity is actually the upper limit. I'm going to make that note at the very bottom here. But going through the motions here, we have then A minus lambda 2I is equal to the matrix 2, negative 3, 1, negative 1, 0, 1, negative 1, negative 3, 4. And that turns out to be row equivalent to 1, 0, negative 1, 0, 1, negative 1, 0, 0, 0. So in the interest of saving time, I'm just giving you the RREF form. That tells me that for row 3, x3 is free. For row 2, x2 is also equal to t. And for row 1, x1 is also equal to t. And that means either the solution to A minus lambda 2I times V equals 0. This system has the solution V vector equal to any multiple of the vector 1, 1, 1, or we might say one of two things. Either eigenspace 2 is the set of all multiples of the vector 1, 1, 1, where t is any real number. But that's the same thing as saying that this is the span of the collection 1, 1, 1. That is to say, the collection 1, 1, 1 is a basis for eigenspace 2. So I'm just really saying the same thing over and over again. I'm not really giving you guys different ideas here. I'm just talking about this language in different ways here. Okay, so what does this mean for us? Well, so first of all, results. A was 3 by 3 and has a total of 3 eigenvectors. And those eigenvectors are the collection B equal to, let's see, what were they up here? Negative 3, 1, 0 is one possible eigenvector. 1, 0, 1 is another one. And then this third one, 1, 1, 1 from the other eigenvalue, together generate what's called an eigenbasis for R3. So remember that, remember that the dimension of R3 is equal to 3. And here we have 3 linearly independent vectors from R3. And this means that not only is B a basis, but B is now a basis consisting of eigenvectors for R3. This is called an eigenbasis. Now, why is that important? Well, number one, since we have a basis, every vector in R3 can be written as a unique linear combination of these basis vectors. And that means that we can simplify any matrix algebra involving A, the matrix that we started with, using scalar algebra. By scalar algebra, I mean eigenvalues. So again, A sub n times any vector is then lambda to the n times that vector. So that coincides with the example that we talked about in the previous section where we were doing our arithmetic and we were changing our matrix algebra to our scalar algebra. And so this eigenbasis here is terribly important for that kind of work. And we've already done all this kind of work in the previous section. I'm just giving names to everything now. So that's going to conclude our first lecture in this section.